Okay, hi everyone. Welcome to another session of the GOCC. Today we have Kim Harry from University of Wisconsin-Milwaukee, and she'll be talking about this, which is a Q analog of constants with multiplicity formula and the product of Fibonacci numbers. Before we start, let us recall our guidelines. We're all learning. No one has all the answers, and everyone has something to contribute. And with that, let's see what Kim has for us. Take it away.
All right. Well, thank you so much for letting me be able to talk here in this colloquium. And yep, like it says on my titles, I will be talking about the Q analog of Kostant's weight multiplicity formula and how we get some product of Fibonacci numbers. Oh, whoops. There we go. Okay, so here's my outline for today. So just so we all are somewhat on the same page, I'm going to give kind of like a little bit of a background with definitions and examples. Then I'm going to give some motivation for my research, like what was the story before I jumped into my results, and then I will talk about my main results. So then I have a q-multiplicity of a positive root in the adjoint representation of SLR plus 1 is always going to be a power of q. And then in this case, we will see that we have a product of two Fibonacci numbers. And then I will end with what is currently happening. So we kind of have this fun timeline where it's like we show what was happening, what happened, like what am I doing, and then what's the future for this project. Okay, so let's look at just the first thing that we would like to know is integer partitions. So let's recall that integer partitions are a positive integer n, and we are looking at tuples, and we're going to arrange the tuples in weakly decreasing order, and the tuples need to sum up to n. So these are integer partitions. So let's look at an example. So I kind of just picked n equals 5 because I thought it was kind of fun because it's not too big, but then like it's big enough to see like the patterns. So if we look at n equals 5, I know we're all kind of muted here, but it's okay. I'll ask like the question still. Like, what is a way we can write n equals 5 where we have it as a sum of numbers that is arranged in weakly decreasing order? So hopefully, I gave this talk yesterday and someone's like 5, and I'm like, yep, 5 works. But we can think of it, and we can think of all these different options. So we have 3 plus 2. Notice that we have it arranged in weakly decreasing order. 2 and 2, 2 and 1, that adds up to 5. So these are all the different options that we can think of integer partitions. Okay, so let's talk about a vector partition function. So here we have a matrix that is a M by D matrix, and we can compute the value of the integer partition function by this phi here. And this just tells us the number of ways where we can write B, the vector, as a non-negative integer linear combination of the columns in my matrix A. So kind of just like partition functions, integer partition functions, we are counting different combinations of writing it up. So integer partition functions, those are just counting the number of ways one can express integers as non-negative integer linear combinations of positive integers, and the same way as vector partition functions. We kind of have like this, it's like counting game happening here. Okay, for my talk, I will be staying with my Lie algebra of type A. So I will call it type A. Sometimes I'll reference as SLR plus 1, but really let's just refresh ourselves with what does this mean. So if I'm looking at SLR plus 1, I have a matrix, and the trace of that matrix is going to equal 0. So that's what I'll be working with when I'm looking at my Lie algebras today. But before we get into that, I wanted to kind of go into like my notation. So far we can kind of been talking about matrices and vectors. So if we think of our definition here for a simple root, well, I'm looking at E, where it's a standard basis element in my R. to the r plus 1. And you can think of E as like these vectors where the ith place is a 1. So when I'm looking at my simple root in type A, I'm going to think of it as alpha sub I, which equals E sub I minus E sub I plus 1. So these alpha sub i's, they're going to have a 1 in the ith place and a negative 1 in the I plus 1 place. So from now on, instead of talking about vectors, I'm going to be looking at my roots basically as this alpha element. And for me, it just is easier to work with. I know we can always go back to matrices and vectors, but for the purposes of my work, I stick with the alphas here. So we have simple roots, and we also have other types of roots. So we have positive roots, which include the simple roots. And notice simple roots are just a single alpha. So alpha 1, alpha 2, all the way up to alpha r. That's in my type A. That's what a simple root will look like. Different types, simple roots look a little differently. But anyways, here for type A, they just look like a single alpha. Then we have my positive roots, which are my simple roots, plus it's a sum of alphas that are consecutive. So notice I have an alpha sub I plus an alpha sub I plus 1, all the way up to alpha sub j, and this can range between 1 and r. Later in my talk, I will be mentioning negative roots, so I just want to introduce that here. So negative roots are just my positive roots, but with a negative sign in front of it. And so really those are positive roots and negative roots. They're very similar, but when you put a negative, some things change. So we'll talk about that later on in my talk. And then lastly, the one notation I do want to point out, because I'll be using it quite a bit in my talk, is the highest root. And the highest root is when I'm taking my sum of alphas, but it's all of my simple roots is what I'm basically summing. So I'm going to notate it like this. But then I'm going to just remind myself that it's always alpha 1 plus alpha 2 plus all the way up to alpha r. So let's look at an example. So let's look at type A2. So again, this is SL3. And I want to look at my simple roots. So like I said before, we can think of them as vectors. So here, my simple root for alpha 1, if we're looking at alpha 1, notice in the 1 place we have a 1, and then in the second place I have a negative 1, and that was the way I was defining my alphas. And then here for alpha 2, I have a 1 in my second spot and a negative 1 in my third spot. So for moving on from now, I'm going to always just say it's going to be alpha 1 comma alpha 2. Those are my simple roots in type A2. And then notice the roots, just all the roots that I have have alpha 1 plus alpha 2 plus the highest, which again, we can think of it as alpha 1 plus alpha 2. And I also have the negative roots. So I have negative alpha 1, a negative alpha 2, and then a negative alpha 1, negative alpha 2 added up right there. So these are the roots. So hopefully they make sense because we will be talking about them. Let's keep moving. So my result, we will be looking a lot about Kostant's partition function. So I just want to explain what is Kostant's partition function. So if I have chi, which is in the weight lattice, the Kostant partition function is this p of chi, and this is just the number of ways of writing chi as a non-negative integral sum of positive roots. So hopefully this is like kind of like when we're always talking about this like phrase here, we had integer partitions, then we had vector partition functions, now we have this. So again, it's kind of just like all the different ways we can count something with positive simple roots. But let's look at an example. So here, I'm going to say, let's find the Kostant partition function for 3 alpha 1 plus 2 alpha 2. And the way I like to think of it is I'm taking all of my positive roots and I'm just labeling them out as like we want to add them up, right? So then I put in a variable in front of each one, and then I say, okay, well, what are different ways I can write 3 alpha 1 plus 2 alpha 2, where it will work out to be that. So here I think of it, and the first one I always think of is, hopefully the one we all thought of right away, I can just put a 3 in front of my alpha 1, a 2 in front of my alpha 2, and then a 0 in my alpha 1 plus alpha 2. So that's one way of writing this. Another way would be putting a 2 in front of my alpha 1, a 1 in front of my alpha 2, and then a 1 in front of alpha 1 plus alpha 2. Because if I add up my alpha 1s, notice I have 2 of them here, I have 1 of them here, so that gives me my 3 alpha 1. And then the alpha 2s, I have 1 alpha 2 here, I have 1 over here, I add those up and I get my alpha 2, or I get 2 of my alpha 2s. And then lastly, we can think of it as putting a 1 in front of my alpha 1, a 0 in front of my alpha 2, and then a 2 in front of the alpha 1 plus alpha 2. So notice here, there are 3 different ways of computing the constant partition function for 3 alpha 1 plus 2 alpha 2. And I also want to just point out there are no general formulas for the constant partition function. Yeah, it's been, I think, looked at for a while, but like there's no way of having a general formula for this as of right now. Okay, another thing that I talk about in my research is the Weil group. So the Weil group is isomorphic to the symmetric group on r+1 letters, and it is created by reflections, and I like to label the reflections as S sub I, and these reflections are through hyperplanes that are orthogonal to the simple roots of my, or simple roots, which I label as alpha sub I. So I have all my simple roots. Remember, those are just the single alphas. And then I have these S's, which are orthogonal to these roots. And I like to picture it like this. So here's an example in type A2. And I noticed that I wrote out all my roots here. So I have a alpha 1, I have an alpha 2, and then I have my alpha 1 plus alpha 2. And notice that I am creating my S sub i's because with the perpendicular alpha sub i's. So if I look at alpha sub 1, the S sub I is perpendicular to that one. And so if you think of it, if you reflect your alpha 1 about S1, you should be getting a negative alpha 1. And notice with like the alpha 2 as well, if I'm looking at that, I have an S2, which is perpendicular to it. And so notice that I have them listed out below, all the elements in the Weil group here. So of course the identity is always there, and then we have like our single S's, and then we have the some multiplication of S's, and these are reduced words here in the Weil group. And no surprise here, I know that the cardinality of this group in this example is 6, because if we think about it, we said it was isomorphic to the symmetric group on r+1, so 2 plus 1, which is S3. So we know that the cardinality of the symmetric group on 3 is 6. So we'll be looking at the Weil group quite a bit today. And then another definition that I want to talk about before we get into too much more is the constant weight multiplicity formula. So this tells you the multiplicity of a weight in the irreducible representation of SLR plus 1 with respect to the highest weight lambda. And you can compute this with this M function. So lambda is going to be always the highest weight. Mu is just going to be some weight that we're looking at. And then we have this alternating sum. So there are a few things in the alternating sum that I didn't define yet. So let's talk about it. So I have rho, and rho is going to be the sum where I am taking all of my positive roots and adding them up and then dividing it by 2. So we'll see that in an example in just a second. How does that work? But just think of it as like if we're just taking the simple roots and the positive roots, adding them up, and then dividing it by 2. W here, I notate that as the Weil group. So there you go. And then L of sigma, well, that's the length of my sigma. So remember the Weil group are these reflections, these S's, and I kind of just think of it as like, what is the length of sigma? Well, I asked myself, how many S's do I have in my sigma? And then that tells me the length. And then lastly, of course, we just talked about it, P of chi, or P of what we have here, is just the constant partition function. Okay, so let's look at an example. So if I'm looking at an example, and I'm going to stick with type A2, so lambda, remember, is always the highest weight. So I notate it like this, but then I also just think of it as it's alpha 1 plus alpha 2. And then I decided I'm just going to pick a mu, and mu here is going to just be alpha 1. And then let's look at how we're calculating rho. So rho, again, like I said, was the sum of all the positive roots. So if I look at that, I have my simple roots, alpha 1 plus alpha 2. Those are the two simple roots. And then notice I have then the highest root left that I have to add in to make it my complete positive roots. So I add them all up together. So notice you can see that I get 2 alpha 1s and 2 alpha 2s, and then I just divide that by 2. So when I look at rho, it simply reduces down to alpha 1 plus alpha 2. And then now let's compute the constant weight multiplicity formula. So here I wrote it out just to remind us like what goes where. So if I have lambda, I'm going to have lambda be my alpha 1 plus alpha 2. Mu is going to be my alpha 1. And so I plug those in accordingly. And then I also will plug in rho, and rho is alpha 1 plus alpha 2. So if I add these two up, well, I have 2 alpha 1s and 2 alpha 2s, so that's what happens here. And then notice that I have an alpha 1 here, or negative alpha 1 from my mu, and another negative alpha 1 from my rho. So I have negative 2 alpha 1s and a negative alpha 2. So if I want to compute this, I have to look at elements in the file group. So let's look at just the first one, the identity. And so if you plug the identity in, notice when I look at the length, well, how many S's do I have in my sigma? I have none. So then therefore my length of this sigma is going to be 0. And then I plug in 1. And here, notice the identity doesn't change anything in this parenthesis, so it comes along and it doesn't reflect over anything. So then I can just simply think of it as, okay, I have 2 alpha 1s plus 2 alpha 2s minus alpha 1 plus alpha 2, and we reduce it down, and we just get the constant partition function of alpha 2. And then you can ask yourself, well, how many different ways can I write this as a sum of positive roots? Well, I only have one alpha 2, so the only option I can do is put a 1 in front of my alpha 2. And then I have one way of writing it. So that's the first part of my constant partition, or my cos's weight multiplicity formula. Sorry. So let's look at another element in the vol group. So I want to look at my sigma S2 times S1. And I'm going to do this with the picture just to see like how are things playing around in here. And I'm just going to look at the constant partition function. So notice before I had a 2 inside this parenthesis because I said I had 2 alpha 1s and 2 alpha 2s. Well, by linearity, I can just pull the 2 out in front of my my sigma, and things work out just the same. So then when I look at this, I can also by linearity take my sigma or my S1 and apply it individually to my alpha 1 plus my alpha 2. So then if I'm applying S1 to alpha 1, like I said before, if I'm reflecting about S1, I get a negative alpha 1. And then if I'm looking at S1 with alpha 2, I take alpha 2, I reflect it about S1, which gives me the alpha 1 plus alpha 2. So here we can see I get a negative alpha 1 and I get my alpha 1 plus alpha 2 when I apply my S1. And then you can combine like terms. So of course I get S2 of alpha 2. And if I think of it again, I'm taking my alpha 2, I reflect it about S2, and I get my negative alpha 2. Okay, so then now I have 2 times a negative alpha 2 minus 2 alpha 1 minus alpha 2. Here I have 2 alpha 1s, or 2 negative alpha 1s, and another negative alpha, or negative 3 alpha 2s. And if I asked you, well, how many different ways can you write this as a sum of positive integers, right? We want positive integers in front of my positive roots. There is no way to do that. So therefore, the constant partition function of this file group element is going to be 0. Okay, so then we did our identity here, and we also did the S2, S1 element, but notice we had 6 of them. We had to do it to all 6 of those. And as you see, everything except the identity is 0, right? Because they all have a negative inside of the constant partition function. So you can't write that as a sum of positive roots. Also, I like this is kind of silly because they're zeros, but I wanted to show like the alternating sum bit here. So I have the -1, and notice when I have S1, well, how many S's do I have? What's the length of that sigma? It's 1. So I wanted to show that like the negative comes along, even though it's a 0. And I just wanted to point out like, okay, we have 1 minus 0 minus 0 plus 0, right? Because the plus comes with the fact that this has length 2. So I wrote that all out, but really all we have to know is like there's one element that contributes, so the constant weight multiplicity formula is 1. Oh, I see someone has something in the chat. Yeah, so here the weight that we're looking at, yes, it is. We can think of it as vectors, but like again, I said earlier, I always think of them as these alphas, and they can be the simple roots. They also can be positive roots. So we'll see that in a little bit, but that's a really good question. You can think of it as vectors, and I think I did do these examples as like vectors, but then I realized they kind of got like really hairy. And so I was just like, you know what? I'm just going to think of them as the alphas. So, but that's a really good question. You can think of it as vectors, but for the purposes and the ease for me, I think of them as these alphas. But yeah, that's a good
Great.
question.
Thanks, Kim. Also,
Mhm.
just a follow-up, sorry, Aditya.
Yeah.
When we say weight lattice, what type
Yeah.
of object is that?
So the weight lattice, I believe, is constructed with these alphas, and like it's kind of like the points where like when you add them all up, like you get this like lattice. And so it's just the points. So if you have an alpha 1 and then you have 2 alpha 1s, like you go alpha 1 away and then 2 alphas. And so you're creating like this lattice. Yeah. That's
Awesome.
another good question.
Thanks.
All right. So my example of the constant. Yeah.
Sorry,
One more
a small.
question. Mhm.
So what is this multiplicity function doing? Is it extracting like the coefficient of alpha 1 in alpha 1 plus alpha 2, or?
So yeah, so what it's doing is, yes, it is just is you will see in a second because I talk about the Q analog, and this
Okay.
I believe does come up again, and it says like, okay, there's one way of writing it in this way. Yeah.
Okay.
Yeah, another good question. And if it doesn't make sense when I get there, let me know. Yeah, we will be talking about the Qs. So okay, other questions? All right, then let's keep going. Oh, there we go. Okay, so notice, like I pointed out in the last slide, only the identity contributes. And when we're looking at the constant weight multiplicity formula, we have to check all of the elements of the Weil group, right? So that takes a lot, especially when we know the fact that the group here grows factorially. So like we have to check all of those. And once we get like past 2, like it grows really fast. So we have this question of, well, what elements actually contribute non-trivially? So here we have this definition for the Weil alternation set. And again, this is just the set that tells us like what elements are giving me the constant partition function as being greater than 0. So which elements of the Weil group are actually contributing non-trivially? So if we look back at my example from above, we said the identity was the only one that actually contributed. So here, my set here is just the identity element. And then when you look at other, like other types, or I shouldn't say other types, but like type A3 or whatever, you start to see that like the elements here of the alternation set start to also grow a little bit. Okay. So what is known about the alternation set so far? And this is kind of like the history part of like, okay, what came before my research? So back in 2012, Dr. Harris looked at type AR and had lambda being the highest root and just picked mu to be 0. All right. And she found that when you look at the alternation set, oh, there should be cardinality bars around my alternation set. But when you look at that, we get a Fibonacci number. So that was known back in 2012. And then in 2017, they decided to look at just type A2 and said lambda is going to be my dominant integral weight and mu is just in the weight lattice. And they found that alternation set was known as well. And then finally, in 2020, they decided let's look at the different types. So type B, C, and D, when mu is equal to 0, they found all of that here. And I wanted to point out that lambda here is the sum of all simple roots in this situation. Because if you think about it in the different types, it's not lambda won't be the highest root anymore. I see one more question. Okay, so yeah, so when we're saying the coefficient, I'm saying sorry, it wasn't the coefficient in front of my alphas, it's the coefficient in front of my q, which tells me like how many different ways I can write it.
It was
Yeah.
a different comment. What is
Oh, okay.
the 0 here?
Oh, 0 in this situation here?
Yeah, so we talked about like the weights were alphas.
Right. So we're just saying like we're at the origin of the root lattice. So we don't have an alpha 1 or alpha 2 or alpha 1 plus 2. We're just like at that center and we're just like finding out everything in the root lattice. Yeah.
Okay.
Okay. So now here we go with the constant, the Q analog for this. So again, it looks like the constant weight multiplicity formula, except now I'm creating this polynomial that has Q's in it. And here, the coefficient in front of my Q's tells me the number of ways that I can write my sigma alpha 1 plus rho minus mu minus rho with exactly I positive roots. So this, I think, is kind of going back to the question of like, okay, like what is the constant weight multiplicity telling us? So it's just the number of ways we can write it. So here, let's look at an example, and we want to calculate the Q analog for this. So again, we have 3 alpha 1s plus 2 alpha 2s. And here, when I look at my example again, so we know we have a 3 in front of my alpha 1 and a 2 in front of my alpha 2. Well, how many positive roots did I use to create this? Well, I used 5, right? There was 3 alpha 1s that I looked at and then 2 alpha 2s. And then notice that if I'm looking at my other one, so if I used 2 alpha 1s, I used 1 alpha 2, and then I used 1 of the alpha 1 plus alpha 2. So there's 4 positive roots. And so then when I'm creating my Q analog here, I said there's one way of writing it with 5 positive roots. There's one way of writing it with 4 positive roots, and then one way of writing it with 3 positive roots. And the coefficients can change because I'm using just the specific example here. Like we could have other numbers in front of my Q's. That just means there was other ways that we could have created something that had 5 positive roots or 4 positive roots. But in this situation, there's just one way. Okay. So, like I said, Dr. Harris looked at when mu is 0 and was looking at SLR plus 1 and said that the cardinality of the alternation set is the R plus 1 Fibonacci. And here I'm going to say the first and the second Fibonacci number are going to be 1. So I know sometimes, depending on who you're looking at, they will slightly change what they mean by F1 and F2, but here both F1 and F2 will be equal to 1. So the cardinality of the alternation set in this situation is just a Fibonacci number. And when she looked at the Q analog, she found out that the Q analog is just the sum of Q's where the exponents of them range from 1 to R. So I don't think we were expecting a slight history lesson here, but I wanted to point it out just because I thought it was cool. Fibonacci is not the first person to have found the sequence. Pingala, who is an Indian poet and mathematician, found the sequence just, a little bit before in like 300 BC. So Pingala doesn't fully get the title of finding the sequence. Fibonacci does, and I'm going to always refer to the numbers as Fibonacci numbers, but I like to point back to like he wasn't the first one to find it. Pingala actually, I think, is, from what I found in the history, was the first person to find the sequence. But anyways, fun fact. There we go. All right. So then after we're looking at Dr. Harris's work, this is where I come in and I say, okay, you picked mu to be 0. What happens if we pick mu to be a positive root? So what do we find out about the alternation set, and what do we find out about the Q analog? And so what I found out was, when I'm looking at my alternation set, I actually get a product of Fibonacci numbers. I get the ith Fibonacci, and I is coming from the fact that I'm picking my alpha sub I here. So I know if I have my positive roots, I know my I based off of my first term of the positive root, and then it's multiplied by the r minus j plus 1 Fibonacci. So r is coming from, well, where are we? What type are we looking at? J is coming from the last term of the positive root, and then plus 1. So I found that that was a product. And then I also found that when I look at the Q analog, mine simply reduces all the way down to just Q, Q to some power. So it's kind of interesting to see that I have a lot more elements in my alternation set, whereas Dr. Harris just had something a little bit smaller. But then when I look at my Q analog, I have a lot simpler Q analog, whereas she had a sum of Qs. So I think it's kind of fun as far to see like that flip-flopping. The more elements you had in the alternation set somehow reduces the number of terms you have in your Q analog. Okay, let's look at like just an example of what I mean of how nice this turns out. So like I said, we're looking at type A, and so I said, let's pick 14. So 14 factorial is a really large number, and if we were just looking at the vowel group, we would have to check all of those elements, which would take a really, really, really long time. But if we look at my my theorem I find that, well, if I'm looking at a certain positive root, so I said, let's look at alpha 7 plus alpha 8 plus all the way up to alpha 12. If I look at that, I know that I have the 7th Fibonacci times the 3rd Fibonacci, which tells me I really only have 26 elements of the vowel group actually contributing non-trivially. So that reduces checking all of these, like really big number, down to I just have to check 26 of them. And then I look at the Q analog and notice that the Q analog just reduces down to Q to the 8. So it looks nice. Yeah, so this is just an application of like, what does my theorem actually say? Okay, so let's prove my product of Fibonacci theorem. But before we can do that, we have to find the characterization of the elements. So I had to look at this and I said, let's fix my I and j between 1 and r. And I said, then if I have a sigma that's in the alternation set with my mu being a positive root, this happens if and only if my sigma is a 1. Or is this product of s's, where the subscripts of the s's have to be a collection of non-consecutive integers, and they have to satisfy the fact that, like, notice like I kind of clump them into like my s's before, so like L1 and L all the way up to LK have to be between 2 and I minus 1. And then the last like set of s's that are possible have to be between j plus 1 and r minus 1. So I have to somehow find the characterization of these elements. And I see another comment. Let's look. Yeah. Yeah. So anyways, let's look at like this proof. So if I'm looking at the proof, I'm going to assume the hypothesis. So I'm going to assume we fix I and j, and we're going to have sigma be in my alternation set. And I want to prove it by contradiction. So I'm saying, what if it's not this way that I'm saying it has to be, these products of s's? What does sigma have to be? So sigma has to be either S1, because notice I don't include S1 in my theorem, or it has to be SR, again, for the same reason I don't include 1, or it's the product of S sub n times a S sub n plus 1, or the other way around, or I have this S sub y where it's between I and j. And so notice like that was like the gap in my theorem where I'm like, I can't pick I and I can't pick anything but all the way up to j. So it has to be that. So if we're looking at those, let's look at case 5. So what happens with case 5? So I'm just going to say, let's look at sy. I'm going to plug it in for my sigma and see where do we break. So if I apply sy to my highest root, I always get my highest root out. And then if I apply it to the row, I get row minus an alpha sub whatever my subscript for the s was. So alpha sub y. And then again, you have your minus row minus my mu. And my mu here again is just a sum of positive roots that are consecutive. And so then I combine things. So notice the rows kind of cancel out. So now I just have a highest root minus my alpha y minus my mu. And this is where things start to break. So I have all of my simple roots, if I add them all up, I have it here in my highest root, and I can take away this like middle chunk that I have from I to j. And then notice that I said y is between I and j. So I'm subtracting a y from this group here, but I'm also subtracting another one here. So then now I get a negative alpha sub y. And this is where we know if we just see one negative popping up in the Kostant partition function, there's no way of writing this as a sum of positive roots. So therefore, here I know this is 0, but I said, well, it had to contribute. It must be an alternation set. So this is where I get my contradiction, is with this negative in front of my alpha. So I know S sub y is not in the alternation set, and by the proposition 3-4 from Chang, Harris, and Ensko, I know that if I have a sigma that contains S sub y in its reduced word expression, that is not in the alternation set. So then I can conclude that anything that has S sub y in its subword is not in my alternation set as well. So if you look at this case is this the one I picked, but like all the other cases have a very similar feel to them. And yeah, they all like you'll find a negative in front of whatever alpha that you apply with your S, so that we get a contradiction for all 5 of those cases. And then if you go with the backward direction, it's just a straightforward proof. You're plugging in 1 or you're plugging in these S's and you see it works out. So by both directions, we've proven that I know the characterization of these elements in my alternation set. And then lastly, before I can prove my Fibonacci theorem, I have to know the number of ways of selecting subsets from 1 to n consisting of non-consecutive numbers. And this is a theorem, I call it my Fibonacci theorem, but it really just means the number of ways to do that is the n plus 2 Fibonacci. And this is an induction proof. So you just, prove the number of ways of selecting it non-consecutively, you find that it is a Fibonacci. So then by my characterization theorem and my Fibonacci theorem, I can prove that the cardinality of my alternation set is this product of 2 Fibonacci. All right, let's look at my Q analog. So the Q analog, I say, reduces down to just Q to R minus, and I like to think of I minus J plus 1 as like the height of my positive root, right? Because I'm just saying like, well, how many alpha terms do I have in my positive root? That's really what this part is saying. So let's look at how we can prove this. So I'm picking mu. I'm going to say it's in my positive roots. And notice that when I look at my Q analog, I'm looking at everything in the vial group. But remember, we can reduce that down to just now I'm looking at everything in the alternation set because I want to pick everything that is contributing that contributes non-trivially. So here I have that. And then there's going to be 4 cases that I have to consider for my mu. I have to consider the fact that I have a mu where it goes from alpha I plus all the way up to alpha j, where I and j can be between 2 and r minus 1. Or I have my mu where I have an alpha 1 plus all the way up to alpha j, where j can be between 1 and r minus 1. Or I have case 3 where I have alpha I all the way up to alpha r. And then my 4th case, which is just my highest root, where I have from alpha 1 all the way up to alpha r. So let's just quick look at case 2. So case 2 is when I have alpha 1 plus alpha 2 all the way up to alpha j. And here I have to consider this s sub j plus 1 element. And I want to know, is it in my sigma or is it not in my sigma? So when I'm looking at this, we're going to first consider that s sub j is not contained in my sigma. So I was, I guess, being very clever and saying, well, I'm going to notate that as sigma is in this n group where it doesn't contain that. So I put it n for no. And then I looked at the Q analog here. And between the left side and the right side, a lot of combinatorial things happen. But the main thing I want to point out is we do simply just reduce down to this sum, where I have q to the t, where t goes from 1 to r minus j. And then I have to consider the other case where, okay, what if s sub j plus 1 is contained in my sigma? So then again, I put a y for, yes, it's in there. And so then again, like before, a lot of combinatorial things happen between my left and my right side of this equation. But then what we want to point out is the fact that I have a negative sum of q to the t, where t ranges from 1 to r minus j minus 1. So because both of these case 1 and case 2 are disjoint, I can add them together. And so when I add them together, notice that I have my sums and they reduce down to simply q to the r minus j. And remember, I said I like to think of like the minus whatever as like the height. Well, if we think about it, how many alphas did we have in my mu? We had j alphas. So that's how we look at it. Or we can think of it as, well, it was j minus I plus 1. So minus 1 minus plus 1 gives me 0. So we still satisfy it either way. But anyway, so this is my Q analog proof. So now comes to the point where I have had a past of what was going on with this research, what I have contributed to this research, and now we're going to move into, well, what's coming next. So notice that we had mu equals 0, we had mu is a positive root, but now I was asked, well, what happens when we have mu as a negative root? So I plugged things in and kind of found this little pattern. So I found the Q analog now is not just simply a Q to the power, but it's like a 3-term polynomial. And I could figure out that the exponents were somewhat related in this way. So this conjecture says, okay, if we have my highest root in SLR plus 1, and I'm looking at a negative mu, or a negative weight, or root, sorry, a negative root, I get this Q analog. And here's just a little bit of an example of like how we can see like this conjecture working out. So if I have the negative highest weights, I can tell you the elements of the alternation set, and then you can also see that I do get this 3-term Q polynomial, and it satisfies the above. And the same thing with like, I've just picked a negative alpha 1 plus alpha 2. You can kind of see the same like way how the exponents of my variables change with each of them. So I was able to take my research, present it at an MRC this summer, and present it to a group of collaborators and said, like, this is what I've done. This is kind of like what I'm sort of seeing for a Q analog. Let's see if we can find more information about this. So when we looked at this, we were just looking at all the negative weights, but right now, currently, we just have things for the negative highest weight. So let's like negative alpha 1 plus negative alpha 2 plus all the way up to negative alpha r. So this is one of our propositions that we've found this summer. So if we have mu being the negative highest weights, we are calling these allowable subwords. So what can we see in the alternation set? What is possible? So we know the identity, of course. And then we have our S sub k, where k ranges between 1 and r. And then we also have like these products. So it's kind of interesting. 3 and 4, I didn't see that in my positive roots, but they're appearing here in the negative roots. So it's kind of cool to see like things changing slightly, but not like the game still is played the same way. But anyway, so these are our allowable words. So let's look at the proof, and we're going to look at case 3, where we're going to say sigma is my s sub k plus 1 times s sub k. And that ranges between 2 and r minus 2. So like before, I put it in for sigma, and I just play the same game. I say, okay, I'm gonna hit my highest weight with my rho by sk, and again I get the highest weight plus rho minus an alpha k, and then I do the same thing with s sub k plus 1. I get my highest weight, I get rho, I get the negative alpha k plus 1 minus, and then if I'm looking at this, the rule was like when I was reflecting about, I should get 2 alphas. So it's alpha k plus 1. I combine like terms, and I notice that now I have 2 of my highest weights. I'm subtracting just 1 alpha k, and I'm subtracting 2 of my alpha k plus, or alpha k plus 1. And then notice that I don't have an alpha k in my final answer, but everything is positive, and that's what I want, so I know it's allowable. So you do a similar thing with the other cases, but you can write these now as a sum of positive roots. Also, we wanted to know what was allowable, but then we also want to know, well, what words are forbidden, or what subwords are forbidden. So here we have this theorem where we kind of look at like all the different possible S combinations that would cause problems in my alternation set. So if I apply something that has this in this subword, I know that that won't work. So let's look at one of them where I'm looking at S sub I minus 1, S sub I, and S sub I plus 1. Again, we play the same game. We put it through there. And if you look all the way down here, I have my highest weight. So I have 2 of those. It doesn't matter that I'm subtracting 2 alpha i's because that doesn't cause any problems. It doesn't matter that I'm subtracting an I plus 1, right? Because I have 2 of them. But the problem comes when I'm looking at my alpha I minus 1. So I have 3 of those. So I'm subtracting 3 of them from here, which gives me that negative in front of my alpha I minus 1. And that's where I have the problem. So I can't write this as a sum of positive roots. So I know that this is not contained in my alternation set when I'm looking at mu being a negative highest root. Okay, so that's what we have proven so far. The goal here is to prove when we're looking at our negative highest weights, we know it's an element of the vowel group. This is if and only if it's commuting product of basic allowable subwords that I said up above before. But anyway, so we still have to prove this. It's coming along, it's almost there. We just have a few little more details to tweak out. But what else do we want to know? I never told you guys what the cardinality of the alternation set was for this. So we would like to prove the cardinality when mu is the negative highest weight. But then also, we haven't covered all the negative weights. We want to know, well, what happens if I have like a negative alpha I all the way up to alpha j? What allowable words are for that one? And then same as like the negative weight, want to know, well, what's the forbidden words? What can we not have? And then finally, what is the cardinality of this when I have a negative mu where it's not the highest weight? And then of course we want to prove my Q analog conjecture that we get this. So really there's a lot coming forward, and then like we're working on it and it's looking very promising. So that's what's currently happening. But I kind of like seeing like, well, this is the history of mu is 0. Now mu is going to be a positive root. And now we're working on when it's a negative. So it's kind of like, I think it's cool to see kind of like the progression of like, how does this all play out with different weights? So thank you so much for your time. Thank you to the organizers for letting me talk here. Yeah, if you're curious about any of the details, I like that one proof I said like a lot of combinatorial things happened. You can find it in my paper here. This is on archive, it's accessible. But yeah, so anyways, thank you so much.
Let's give Kim a round of applause. Hey, lots of reactions. So, what questions do we have? Go ahead.
Yeah, hi Kimberly, this is Sheila.
Hi.
Sorry, my video is off because I just got a COVID vaccine and I feel horrible.
I'm sorry. Well, hopefully you
It's
feel
okay.
better.
But my question is, what does this have to do with the Kostka numbers? Like, if you take the Lie group representation,
Mhm.
the irreducible, and
Right.
then you write it out, the multiplicity of a weight is actually the Kostka number. So what's the connection?
Okay. I'm not really familiar with that. I kind of just like in a way just played around with like what I'm finding with the like multiplicity, but like that's something I kind of want to like dive a little bit more into is like how does this relate to other things? So right now I'm not 100% sure on how it relates to that, but I know that's something I want to look into. Just because I'm not fully familiar with everything and I don't want to say anything wrong with
Okay.
like a response
So
to that.
I was
So
just confused because you seem to be using weight and root synonymously, but they're actually duals
they're
of each other.
different, I know, and that was a comment I got the other day where I interchanged them and I really whenever I was saying weights, I really meant roots.
Okay.
Yeah.
All
Yeah,
right.
that's my bad. So it like
Okay.
after I introduced like yeah. So
Okay.
that was on me.
All
I
right.
really just mean roots. So
Okay.
yeah.
Thank you. That's very helpful.
Mhm.
Great talk. Thank
Thank
you.
you.
More questions? Um,
I have a question. Hi, thank you for the talk. In the formula, you use this rho and you defined it as a uh, sum over two. But in all your examples, this goes away somehow after you apply sigma. Rho
Yeah, I
cancels.
was
Is it
yeah.
a feature of rho, or could you have defined it some other way and the same results would come?
Yeah, so as I was like prepping for this, I noticed that as well. I was like, well, is it necessary for me to have rho applied here? And what I think it is yes, we do still need this because the thing is I need to be looking at how do I want to say it? We're always subtracting, like if I'm taking my s sub I, right, and I'm applying it to rho, then I know I'm getting a negative alpha I. And I think I'm not 100% sure because I'm only looking at type A, but I'm assuming in type B, rho does play a little bit more of a role in it. Because when we're looking at type A, notice that like when I'm adding up all of my positive roots, I like there are no numbers or coefficients in front of those alphas. Whereas I think in like type B, like we can see our positive roots having something in front of them. I think B has like a coefficient of 2 in some of the roots that we're looking at. So I think in this situation, it just so happened that rho was kind of canceling itself out. But I think in maybe the other types, I'm not like, and don't quote me because I don't know 100% sure because I only looked at type A. But like I think rho does play a little bit more. But the only reason I want to say we need it is because then that's how we're getting like another negative alpha subscript of whatever element we were looking at. But yeah, I noticed that as well. I was like, oh, well, they always cancel out, so do I really need it? And I think the only reason I really need it is because then it's giving me that negative, like negative alpha being subtracted. But also it is in the constant weight multiplicity formula, like in the like it does happen, so it must be there for a reason. I just don't know like the background of like the full on like why, but you're right, it does. In the end, we kind of just like get rid of it. So yeah, I think it has to do with maybe also like how are the roots changing.
Okay, thank you. Yeah, I just asked myself if you can define it in another way maybe, and this still
Possibly, yeah.
holds, or I suppose my base question is what is rho? Why is this defined like that? But
Yeah.
uh,
I'm not necessarily sure why it's defined like that, because like again, it's just taking all the positive roots and adding them together and dividing it by 2. And it doesn't look nice once you get above A2. Like things get like you get weird fractions in front of your alphas. Yeah, I don't know. I don't know. Maybe if like defining rho is slightly different, like maybe might make the constant partition function easier to work with. I don't know. It's just this is the way everyone like all literature has been working with it. So I didn't want to find another method of solving. Yeah.
thank you very much.
That's a good question. I want to think more about that. Yeah.
I had a question about, so the first coordinate is always, so the first thing that we're looking at is always the highest root.
Mhm.
Have you looked at like a general a root comma root thing? Or like
Yeah,
when, like
I
what
have.
happens?
And has the literature looked at that? I know the way everything I've been looking at always kind of defines the lambda portion as like it has to be dominant, a dominant weight. And so I know they've at least everything I've looked at always has like that as like the highest one. Or I do you remember when I went and I kind of gave a history back in 2020, they looked at different types. Well, that one, lambda actually is not the highest one in that one, because it's just the sum of all the positive. Because once you go to type B, like the highest weight is not, or the highest root is not the sum of all the positives, because we have again like some kind of a coefficient in front of one of them. So I'm sure that is possible to look at it, but I've been sticking with just like let's just fix lambda to always just be that one. And yeah, all the literature I've been looking at always just kind of like fixed it that way. And I don't think they changed it, but I'm sure someone's done something where like they changed it a little bit. But again, that might maybe that's open, and that could be another project to work on. Like that would be cool.
Oh, fun. Yeah, I think we can keep some questions for later. Thank you, Kim, again.
Thank you so much for letting me talk.
Really nice talk. It was great talk. I love having examples in talks.
Oh yeah, I need examples always.
Thank you, everybody, for
Thank
coming.
you